Good morning. I will be presenting our work detecting screen presence with activity-oriented RGB camera in egocentric videos. This work was done in a collaboration with researchers at Northwestern University and Birla Institute of Technology. Our work is a contribution towards detecting screen presence in a real-world setting. Primarily, our study involves tracking the daily interactions of subjects with televisions, laptops, and mobiles. The detection is on an egocentric video captured with a wearable device in a privacy-preserving manner. The broader goal of this study is to understand the relationship of screen time consumption with health risk behavior. During the last 2 decades, wearable technology has added a whole new dimension in the healthcare system by real-time continuous monitoring of human body. They are used in daily activities and fitness monitoring, and also in monitoring the health condition. There are a lot. There is a lot of research and development activities being pursued to develop more innovative and reliable wearable devices. Egocentric videos are often high resolution, and researchers have identified approaches to extract coarse-grained activities of the user and the contextual information from them. Our study involves data that is obtained from a low-resolution, activity-oriented RGB camera from a wearable device called WildCam. The WildCam system hosts a dual-stream RGB camera with a 180-degree fisheye lens. Participants of our study wear this device as a necklace around their neck. It hosts a low-cost, low-power 8x8 IR sensing array. After recording their interactions while wearing the device, the participants return the device, and the data is then further processed offline. This study involves 10 participants, and each of them have captured their daily interactions for 3 days. We have 8 hours of data from each participant, and overall it comprises of 1.2 million RGB frames with 80 hours of video. This data is captured by a 180-degree fisheye lens and recorded in 240 cross 320 pixel resolution. An example image set is demonstrated in this slide, where the participant's face are hidden just to protect their privacy. Data annotation and labeling. So we have worked with 4 trained annotators to generate labels. Each frame was labeled by 2 annotators working from an exhaustive rubric generated through weekly discussions. Overall, we have 300,000 frames labeled with binary labels, which are 0 and 1, screen and no screen. Additionally, we have 24,000 frames labeled on a bounding box level annotation to localize the region of interest. This is the entire training set for our models. Now for an overview of our system. After the annotations and labeling process, the next step is to use a backbone model to extract features of screen presence. The motivation for this step is to use existing state-of-the-art models as a feature extractor. After exhaustively testing the existing benchmarks in screen detection, we decided to choose a backbone with efficient net D7X, pre-trained on the COCO dataset. The last part of our pipeline is the screen prediction network. This network performs the final prediction for screen presence in a given frame. Our system processes the data on a frame level. Our network architecture. So our backbone is able to learn the importance of screen detection features and is scalable across different resolutions. We used efficient net because of the pyramid network, the BiFPN layer, which is part of its architecture. The reason to use COCO dataset as one of the pre-trained features is because 3 out of the 80 categories in the COCO dataset are phone, tablet, and televisions. Also, this backbone is ranked 5th in real-time object detection and 2nd in object detection on a COCO dataset. In this slide, I want to go over the evaluation of our model on a frame-by-frame level and on an episode level. To evaluate on a frame level, it is computing the F1 score for each frame. To evaluate on an episode level, we used an unsupervised clustering method known as DB-scan, density-based spatial clustering of applications with noise. It essentially generates a cumulative distribution function across the data set, and by tuning 2 parameters of the number of positive samples per frame and the distance between 2 positive samples to be clustered into an episode, we generated 112 episodes across our dataset with 81 seconds being the at least 81 seconds of positive screen samples within an episode, and at most 142 seconds between 2 positive samples to be clustered together. Just to go over our performance measures once, our final F1 score at an episode level was 0.81 across 112 episodes, with a precision and recall around 0.8. Further, we also compared our existing works, our model and our system with the other existing works in the literature. So our performance comparison was with object detection benchmarks, which were trained on the COCO dataset, especially YOLO V3 trained on the COCO and COCO minival. And we also trained on 2 benchmarks from the egocentric videos models in activity recognition space, the screen voider and the dead D7X. As you can see, the test performance of our framework was better than the existing pre-trained state-of-the-art in this space. Further, we have also analyzed broad challenges that our system is more sensitive towards. They can be broadly classified into 3 categories: handheld devices, where there is interaction of the human hand between the edges of the screen, having artifacts in the field of view, especially bright artifacts and motion-based artifacts. Also, there is a case of screens at the edges. Given the egocentric field of view of our dataset, the screens at the edges are especially warped in a different shape, and it is difficult to detect them as traditional screens. These were one of the most challenging cases for our system right now. Conclusion. So our system is efficient in tracking the daily interactions with screens for the subjects in our study, televisions, laptops, and mobiles. It also yields an F1 score of 81.81. We have also compared this performance with existing benchmarks, where on a test set of 10,000 images, it yields 0.78. The future direction is to include the additional sensor information from the WildCam system in detecting other activities like eating and social presence. uh, that would provide deeper insight into subject behavior, and we could model the health risk behavior as well. Acknowledgements. So our work is sponsored by the National Science Foundation. We'd also acknowledge support of the National Institute of Diabetes and Digestive Kidney Diseases and the National Institute of Biomedical Imaging and Bioengineering. It is also a collaborative effort between two labs at Northwestern, uh, the Image and Video Processing Lab, led by Professor Katsagalos, and the Habits Lab, led by Professor Nabil Al-Shrafa. Thank you very much, and I am excited. I'm opening the room for some questions.